So far, we've talked about congestion and what its properties are. We tried to make it fit a TCP model. If you recall, we talked about retransmission and its effect. And now we're ready to define the problem of congestion control in TCP. We have distributed endpoints wanting to send information, and we need to decide how much each endpoint sends at a given time. As you may remember, TCP is a distributed protocol, with decisions needing to be made by each point separately. TCP is also a pipelined protocol, meaning there's a window of information which is still in the air without acknowledgement. We saw that one of the limitations on the window size is a limit of flow control, that we can't send more than what the receiver can receive. Let us introduce another limitation as a result of congestion control and discuss window size. Right now, we won't address the limitation of flow control and assume the only limitation that exists is about congestion control. Thus, we need to make the window fit the conditions of the network at the moment. What kind of feedback would we get? There are a few options. We might get implicit feedback or explicit feedback. What is explicit feedback? Explicit feedback means that the network itself would say it's now under congestion, and maybe other parameters that characterize congestion. But that means we need to know how the routers are implemented. However, it is better not to rely on network information and to use implicit feedback. And implicit feedback will tell us that if we got no acknowledgement from a specific host at a particular time frame, that probably means that the packet didn't arrive. And then we need to decide what to do. This is the feedback we're going to use. Which rule would we use to change the size of the window? There are a few options. One of the options is the rule called AIMD, additive increase multiplicative decrease. And what does that mean? Additive increase means that the window size, CWND, grows by a maximum of one segment size every RTT until the packet traffic fails, meaning that we increase the window while we feel there is no congestion. And in case we feel there is congestion, the step we take is multiplicative decrease. One of the examples is dividing the window in half. You can see it here in the picture. The time units are RTT, and the graph shows CWND size. So every time the window grows, it's additive increase, and the moment there's a drop by half, that's a multiplicative decrease. That is what's called the control rule, how the window changes in each of the endpoints. So let's look at a few more details. The way we're used to it, if we're on the entire space of sequence numbers, then we have colors just like when we talked about reliability. And as you recall in Go Back N and Selective Repeat, here too, everything that's green is already acknowledged. And the window that begins with yellow, CWND, this is exactly its size. The yellow ends. This is what's already been sent but not acknowledged. That means it's still in the air. What you're seeing in blue is everything that hasn't been sent yet. What about the CWND size? We change it according to a control rule, like AIMD. It's a dynamic variable. How can we estimate the sending rate for TCP? Approximately, it'll be the size of CWND and how much we send divided by RTT. This will be the sending rate, some kind of estimate of the sending rate within TCP.